For my research topic, I came up with this prompt called dynamic guardrail generation. So for the introduction, large language model often generate bias and toxic content, and why there are many efforts. So while there are many efforts, there are still many disadvantages, such as in terms of the cost, and a lot of current techniques are reactive. Why are reactive, which doesn't really fix the flaw reasoning process that produced the initial output. This results in superficial fix that fail to generalize across different contexts because the underlying flaw logic remain uncorrected. Furthermore, the guidance these methods employ is often abstract, relying on the model's ability to interpret a high-level goal rather than follow explicit instruction. For example, there's this method called self-correct. So after only an direct initial output is generated, and then the model will just correct it, and yeah, sorry. So today I propose the dynamic guardrail generation framework. So this method operates in a black box setting and requires no training. In other words, it doesn't require a lot of cost to implement. Inspired by the principle of structured deliberation, it compels the model to first perform a formal prompt-specific risk analysis and then generate its own explicit imperative safety rules. The model final response is then strictly constrained by this self-generated dynamic guardrails. So the first stage is threat identification. So it will analyze the prompt and list out a certain number of most probable types of bias or toxic content that could emerge in an AI response if answered directly. The next step is I'll provide some examples of it so that the model will have a clear view of what I mean. So the second stage is directive formulation. So in this step, the model task is to convert this abstract threats into concrete imperative behavior rules. Starting with you must or you must not. The last stage is using all this rules, and it will provide the finalized completion for the prompt. So to evaluate the effectiveness of this method, experiments will conduct on ChatGPT of the 3.5 GPT version using RTP high toxicity dataset and bold 1.5K the bias dataset. And the baselines include simple base prompting, pre-hoc prompt, and reactive self-correction. Performance was evaluated using toxicity, bias, and generation quality metrics. So here's the data of the matrix, which include expected maximum toxicity, toxicity probability, and toxic fraction. For bias, it's sentiment-based matrix and a regard-based matrix. For generation, they are perplexity, similarity, and diversity. So for more information, expected maximum toxicity is the highest toxicity scores across 25 final generation samples for specific prompt. Considering all prompts, the toxicity represent the fraction of all prompts for which a toxicity score of 0.5 or higher was generated at least 1 out of 25 sample. Toxic fraction denotes the proportion of all generation sample with a toxicity score exceeding 0.5. For the mean sentiment, the average sentiment score across all groups for sentiment deviation, how much sentiment scores vary from the average. And for the group fairness, we measure how different each subgroup sentiment distribute is from the overall distribution using this Wasserstein-Dwan distance. So a lower GF score means subgroup sentiments are more similar, which suggests less bias in the model responses. So for the results, my method significantly outperformed all baseline methods on bias mitigation, reducing bias metric for gender and race effectively. It also improves generation quality with better fluency and similarity retention. For toxicity, this method reduced harmful content better than base and pre-hoc, but is slightly less effective than self-correction in detoxification. So preliminary findings indicate that this when break this prompt into one single API is much less effective than breaking it into like 3 API calls. And another ablation was conducted to determine the optimal number of the types of that in stage 1 of this framework. So the final result is that 3 is the most effective number. I think it's due to the like the deliberation can be like excessively long, and it can diminish the model's ability to focus on the final generation task. So there are a lot of limitations about my research topic due to time and resource constraints. So the first thing is that this research topic is conducted as a small scale experiment. So the effectiveness of this method is not clearly illustrated. Also, this is only conduct on like limited model selection and also a small number of completions. So this cannot like ensure like good robustness, cannot test on like robustness of this prompt. Okay, to conclude like a very short conclusion. So I believe this does have potential on this does have like a lot of potential, and I believe like future work can be conducted on this to um to sorry so I believe like further work is still needed because this research paper of mine is not really comprehensive enough, and it doesn't cover every single it doesn't cover many models, or it wasn't tests on many data set like. So yeah, so I believe future work still needed. So really grateful to my mentor, Susan Ayas. Sorry. Even though I don't focus on her field of interest due to time constraint, I did learn a lot about driver monitoring system a lot throughout the program. However, as I focus on a certain fine-tuning method to test on this domain, I realized that method can't be conducted given the time constraints. And so at the last minute, I changed to this topic because I believe it will be more feasible to work on. And I'm really sorry, my mentor, for that. Also, I'm really grateful for the Talaria for providing this opportunity for me to learn a lot of things about my mentor field of interest, even though I didn't have like a lot of um even though I didn't really have the opportunity to do any experiment on it. Though I still learn a lot, and I'm really grateful for all the people that create this program. Thank you.